Welcome. My name is Elisa Vainio. I've met many of you already, and I have been in contact with many of you while organizing the event. But today I am here chairing this session. There is a lot of attention to climate change and carbon, both in this meeting and outside this meeting in public. And it's not a bad thing. But I just want to point out here in the beginning that we should not close our eyes from other environmental problems while focusing on tackling climate change. Other environmental problems like biodiversity loss or eutrophication of waters, for example. And this session we have dedicated to the multiple benefits that healthy soils can offer. So we will hear a bit other perspectives besides carbon in this session. First, I want to welcome our first keynote speaker, who is remotely from online, Nico Eisenhauer from German Center for Integrative Biodiversity Research, IDIV. And Nico will tell us about the JENA experiment. This is about the interactions between plant diversity and ecosystem processes. Do we have Nico online? Welcome. Do you hear us well?
Hello, good morning.
Welcome. Do you hear Morning.
Us well? I do hear you well. Do you hear me well? Do you see my slides in the right format?
We hear you well. We see you.
We hear you well. We see you.
Now I hear myself.
Okay.
Now I hear myself.
Yeah, me too. There is an echo.
Everything is fine. Go ahead and start.
Everything is fine.
Stage is
Go ahead and start.
Okay.
The stage is yours.
Okay, thanks a lot. Good morning, everybody. Cheers from Leipzig, Germany. Moving from the youth to me now. I would like to thank all of the organizers, specifically Elisa, for inviting me and working on this important topic. Yeah, healthy soils are actually the key when it comes to biodiversity and climate change. So we should not see these important alterations in isolation. I think there are really important connections between the two. So this is just to refer to the previous introduction. So I was told to talk about the JENA experiment and interactions between plant diversity and ecosystem processes. But given the focus of this conference, I changed the focus slightly, and I would mainly like to focus on plant diversity effects on soil carbon accumulation. And I will focus on the JENA experiment, but I will also go beyond. So first of all, human activities are altering biodiversity and the climate. Looking at the Earth at night, you can see that there are many direct effects that are visible. Indirect effects are almost everywhere. So what this brings is a change in biodiversity at many places, a loss of biodiversity. And the question emerges, what are the consequences of biodiversity loss? And in order to address this question, people have been setting up experiments, ecological experiments, the number of plant species on experimental species, 2 species mixtures, 4 species, 8, 16, up to 60 species. And what we can do on these plots is to study different ecosystem processes. We can study how much biomass accumulates above and below ground, how much biomass can be harvested, how much carbon is in the soil, and many more things, and this will be in the focus of this presentation. Now, the JENA experiment is not the only biodiversity experiment with the setup of manipulating the number of plant species, and there have been many studies on plant biomass responses to gradients, experimental gradients in plant diversity. And this is a synthesis that we compiled several years ago, where we looked at the productivity of these plant communities as affected by the number of plant species in such experiments. What you can see here is a lot of lines. This means that we could use data from 46 different grassland experiments, so it's quite a lot. And what we could also study is different years. So looking at this relationship in different experimental years, including dry years and wet years and normal years. And what we see is that in general, the productivity of these grassland communities increases with the number of plant species, which means that if we are losing plant species at the local scale, we are also losing productivity, which means how much carbon is fixed in the vegetation. We went one step further in this study and also looked at the stability of productivity, here given as the resistance. This means how much does productivity deviate from normal conditions, ambient conditions, when there is an exceptionally dry or wet year. And again, we could see that there is a strong stabilizing effect across these many settings of plant diversity. So the more diverse the plant community, the more stable is the primary productivity. And this is also an important message to land managers and also farmers. If they would like to have stable productivity, then they should also be interested in fostering local biodiversity. But these plants are not alone, and this is depicted here. You can see plants in the center of this complicated network of interactions or potential interactions. There are a lot of organisms above and below the ground that interact with the plants, that respond to plant diversity, but also that feed back, that influence plant performance. And it is really important to consider these interactions among different organisms. So plants are not alone, and changes in plant diversity can have cascading effects on other trophic levels. And this is early results from the Jena experiment that we gained, where we studied different kinds of organisms above and below the ground. And what this complicated figure is supposed to show you is that if you're increasing the number of plant species here in the center, this will also increase the abundance and diversity of herbivores, so invertebrates that consume plants above ground and also below ground. And it has also cascading effects on higher trophic levels, like carnivores, for example, spiders and beetles that feed on the herbivores. So we see a lot of cascading effects across the whole food web, above and below the ground. Okay, so looking back at plant diversity effects, and we have already seen quite substantial responses of above ground biomass production, and this is also shown here for the Jena experiment. We see biomass production above ground as affected by the number of plant species in different experimental years. You should note that 2003 was a very early assessment of plant biomass. This was 1 year after the setup of the experiment at a former agricultural field site. So after 1 year of experiment, we already see an increase of above ground biomass production with the number of plant species. 2 years later, it's also there. There's a little bit of variation among the diversity levels. But starting in 2006, it looks like, stairs going up here in each case, and the significance of effects increases. Now, looking below ground, the pattern is a little bit different. You see that in the initial years, there are not too strong or no visible biodiversity effects, plant diversity effects, but these have to materialize over time. So only in 2006, 2008, and then in 2011, we saw a strong plant diversity effect on root biomass. And I can tell you, although it's not shown here, that this diversity effect is now very stable over time. It's now a decade later, more than a decade later, and these diversity effects are still very pronounced. So it takes some time until the plant diversity effects reaches the below ground world in such an experiment, but also if you have any change in land use, for example, the soil community and the soil conditions have to change over years. This is also what I found for soil microbial biomass, a really important carbon pool in the soil and also a mediator of carbon dynamics. Again, here looking at microbial biomass as affected by the number of plant species in the initial years, you can see no statistically significant plant diversity effect, but then after 4 years, there is a strong diversity effect that materializes, and this is also very stable across time. And this time I can show you even more results. Now we are seeing here basal respiration, so an activity measurement of the microbial community in the soil and soil microbial biomass. And we can see that for basal respiration initially and for microbial biomass, no significant plant diversity effect. And then in later years, this became more and more significant and also it's a quite stable effect. Again, it ends in 2014, but I can assure you that this is still valid. Okay, so more carbon fixed in the microbial community. This is important. We also looked at soil carbon accumulation in the Jena experiment, and we saw that over the first decade of experiment, there was a really strong soil carbon accumulation happening. And this was kind of irrespective of the presence of important plant functional groups like legumes that are shown here. We have plots with and without legumes that play an important role in nitrogen fixation and thereby also has a cascading effect on effects on carbon dynamics. So in each of these treatments, we saw a quite strong diversity effect on soil carbon accumulation. And what this means is that at high plant diversity, we had roughly 3 times more carbon being fixed in the soil as compared to monocultures. That's a quite substantial number. Then we also try to understand the mechanisms of soil carbon accumulation. How is this happening? And this is here shown in a structural equation model. I will guide you through this. So we start with the experimental manipulation of plant species richness. For simplicity, we leave out the legumes for now. They also have important effects, but they are overall less pronounced than the effect of the number of plant species. So with a higher number of plant species, there is also more carbon inputs into the soil. This means litter above ground and below ground. And what we in this study could not measure, this is also rhizodeposits. So other carbon inputs of plant communities into the soil is enhanced with the number of plant species. This is this positive arrow here. It's highly significant. And at the same time, both plant species richness and these carbon inputs stimulate the soil microbial community, more activity in the soil. And this higher activity of the microbes then also drives carbon storage. So it's not the direct link through carbon inputs. It needs the microbial processing of the inputs to be stored in a stable way in the soil. We also looked at different components of soil carbon, and this is now dissolved organic carbon, which means this is carbon that we can measure in soil water solution. And again, we have beautiful time series here across many years, and it's a similar kind of analysis where you see plant diversity effects, plant species richness 1, 2, 4, 8, 16, and 60 on this dissolved organic carbon across the many years. And at the beginning, there was a lot of scatter, not so stable diversity effects, and they became much more stable over time. We can also look at temporal dynamics, even within year dynamics of DOC, this dissolved organic carbon, because we have continuous measurements of that. It's a really unique time series that we can look at. And we can also see if the different seasons vary in, first of all, dissolved organic carbon availability. And we see, yes, the concentrations are higher in summer and autumn. But in all seasons, there is a strong plant diversity effect that we observe. And there's also important effects of specific plant functional groups, but those are less in the focus for this presentation here. Okay, we then also looked at how deep do these effects go into the soil. Is this just in soil carbon accumulation in the topsoil, or does it go deeper? And we measured soil carbon concentrations and stocks down to a depth of 1 meter and in different years. So after 5 years of experiment, 10 years and 14 years. And what you can see here for species richness effects, that you see some blue bubbles, which means some positive effects in the early years, but not so many. Then after 10 years, more significant effects, particularly in the topsoil here. Yeah, it's a really big bubble here, carbon concentrations. But then after 14 years, you see quite strong plant diversity effects on soil carbon accumulation across the soil profile, going really deep, down to 1 meter even. So again, transporting the message, these communities, these soils need time to be able to store the carbon and to react to variations in plant diversity. So what are the mechanisms? How does this work? And we performed a greenhouse experiment in small microcosms to study the role of root biomass and also plant root exudates, their amount and diversity in driving soil microbial communities and processes. Again, this is a very complicated figure. The only message I would like to convey here is that with more plant species, there is higher root biomass. We have seen this before. There's also a higher diversity of roots in the soil. This is also quite understandable, I think. And at the same time, the diversity and the amount of root exudates, so mostly liquid organic inputs into the soil, is increasing. And this is increasing then the bacterial biomass in the soil and mostly the fungal biomass. So there is more fungi with higher plant diversity, and this is mediated by a higher root biomass and amount of exudates that are released. And we tried to summarize this in a little video. First of all, what we saw in the Jena experiment, that we have a substantial difference between low diversity plant biomass production, for example, and on the right-hand side you can see a more diverse plant community. This more diverse plant community does not only produce much more plant biomass, but it hosts a lot of more consumers. You see a lot of invertebrates here, above ground and also below ground. A higher diversity and abundance of below ground organisms. And then when we are looking below ground, we see that these organisms do something. You can see beautiful earthworms pulling leaves into the soil, but we also see that there is plant inputs into the rhizosphere, and with higher plant diversity, there are more exudates and root products being released in the rhizosphere, more microbes accumulating, processing these organic inputs, and then also accumulating carbon in the soil. What we also showed in a different experimental setup is that with a higher number of plant species, there's also a higher carbon use efficiency by the microbial community. So what you're seeing here is that the microbial biomass is depicted here again as affected by the number of plant species. It increases. Also the activity increases with the number of plant species. but then the ratio between respiration and biomass decreases with the number of plant species. And this is telling us that the microbial community at high plant diversity, is more efficient in using plant carbon. Okay, we also summarized information from different diversity experiments, not only in grassland, but also in forest, in wetland. There is much fewer studies in forest and wetland, and we looked at plant diversity effects on above ground biomass production. As you can see in the top panel here, there are significant effects in all cases, grassland, forest, and wetland. For below ground biomass, the effects are very clear for overall, all data put together. Also for the grasslands, it's quite substantial. For the forests, not so much. It's a quite neutral effect here. The effect size is touching the zero line, so there's a lot of variation. But these forest diversity experiments are quite short-term for forest stands, so we probably need to wait longer to see effects. And for wetland, there seems to be a substantial positive effect, but there's also few studies and a lot of variation. When we are looking at soil microbial biomass, again, quite clear effect for grasslands, for forests, not so much, and for wetland, again, a low number of studies. For soil carbon, there's again a lot of variation, and I think what you should note here is that we have really few long-term experiments that can study these relationships, and you have seen that it takes almost decades that these plant diversity effects on soil carbon materialize. So we need to look longer. Okay, so some take-home messages from this presentation. The Jena experiment has shown that there is roughly 3 times more carbon in soil accumulated in high diversity plant communities as compared to low diversity plant communities. And this only within a decade. The longer we look, the stronger the effects get, and we have to do the math again, now also considering deeper soil layers where also carbon is accumulating over time. Then plant diversity increases plant inputs into the soil through roots and root exudates. Plant diversity enhances soil microbial biomass and activity. I've shown that. I can also say that it's also increasing the diversity of the soil microbial community. I did not have time to show that. And it's probably the microbial products and partly their necromass, so dead materials that accumulate in the soil and drive this carbon accumulation. Plant diversity increases the proportion of soil fungi over bacteria, and this increases carbon use efficiency of the soil microbial community. And we really need long-term studies, and particularly in forests, to truly understand the capacity, the potential that high diversity plant communities have in helping us storing carbon in the soil and removing it from the atmosphere. With that, I would like to thank my team. All of this was teamwork. I'm also thankful for the financial support by different funding agencies, and I would like to thank you again for your attention and the organizers for the invitation.
Thank you. Warm thanks to Professor Nico Eisenhauer once more. We would really love to take some questions from the audience, but because there is this problem with the echoing, then maybe it's not possible with this presentation. But we really appreciate that you Nico, could join us in this way and give this keynote talk. I hope that people can reach out to you, perhaps via email or through the Event platform, if they have any further questions or want to discuss with you. Thank you so much, and we will... Thank you, bye. I'm sorry. Really sorry about these technical issues, but maybe we don't take the echoing thing back anymore. So hopefully we will have some time for questions after each of the presentations in this session. And now we have a second keynote speech. We will hear about research on biodiversity here in Finland. And I think it was really nice that we already heard the importance of plant diversity. And now I would like to invite to the stage Jussi Heinonsalo, professor at the University of Helsinki. Welcome, Jussi.
Okay, thank you for inviting me and the TwinWin team to present our first results. And now, where is the presentation? Yeah, my name is Jussi Heinonsalo from University of Helsinki, and I will show data from the whole big team. Well, there is something happening. Yeah, now it looks good. Yeah, great. Okay, and the topic today is the TwinWin experiment, which actually is kind of child of this Jena experiment. We have tried to follow the logic and setup of Jena experiment, and now I saw the first results. The experiment has been going on for 4 years only. So let's see how it looks like. Wait a minute. Yeah. Some words about the history. The experiment was, as I said, established in 2019. That year we got funding from Majan Thur-Nessling Foundation, a Finnish foundation that funds environmental research quite extensively. And it was part of the carbon action platform, and the research aim was, of course, soil carbon. But there in this experiment we wanted also to study how biodiversity impacts soil carbon sequestration. So we make this combination, and there comes the name TwinWin. And in the spring, we got the funding decision about in March, late March, and the growing season was coming really closely. So we really rushed up with the final design, and there we got a lot of help from Professor Bernhard Schmidt, who has been involved in the Jena experiment. That was really, really essential also for our study. I think I will skip most of this slide because Nico Eisenhower's presentation was perfectly telling all these things even in more details. But maybe just some additional words is that while Jena experiment is studying grassland ecosystem, our aim was to transfer this logic into agricultural ecosystems. And as we all know, the intensive agriculture decreases biodiversity. It has negative impact on soil biodiversity and soil kind of trophic network complexity and those kind of things. So now we wanted here to test how the Jena experiment and that logic works in agricultural context. Because of course there is a big difference there that we should also grow crops and make economical profits for the farmers, not only study diversity as such. So that was the scientific background and logic, and therefore we designed this kind of experiment. There you can see on the left-hand side that we have all the treatments we had. So first we had the bare fallow as a negative control, so no plant growing there for whole of the experimental period. So of course that's not relevant in agriculture, but we wanted to have this kind of minus control as well. Then we have 2 different barley controls, so we grew barley over the whole first 4-year experimental period. So we had barley plus herbicide, which is the normal practice used in the agriculture in this region. Then we had barley without herbicide, and all the barley diversity treatments are without herbicides. There, the green, different shades of green show the diversity treatment. So we had barley plus 1 Anderson plant species, or 2 or 4 or 8. So this follows the Jena logic, although we had to stop to 8, while Jena went up to 60. So we work on the kind of lower range of the diversity levels. But anyway, then we had 2 different functional types of plants. those that can fix atmospheric nitrogen and those that can grow deep roots. So we had these combinations with or without fixing or deep root growth patterns. And they were then, there is a laser, I don't know if this, well anyway, we had different underzone richness levels and then functional diversity levels. And they were then distributed evenly in the field in 4 blocks in randomized design. Then comes these blue squares there on the right. So even though we were interested originally on carbon and then we added diversity on top of it, we still need to study other things as well. We cannot focus only on those things as we aim to promote kind of regenerative farming and practices that are useful for the farmers as well. That's why we wanted also to study the quality and quantity of yield, and the quality means in this case plant health, disease suppression or disease levels. Then also farmers' economy is important, and there is team studying economical aspects using this TwinWin field data. Then we also need to study other environmental impacts so that one aspect doesn't compromise the others. So that's why the greenhouse gases were studied, also methane and N2O in addition to carbon and CO2. The nutrient runoff is also important, and that was studied in a kind of separate greenhouse experiment with the same logic, and that data is not shown here today. And then modeling is kind of the aim is that the modeling team can also catch data from our field experiment and transfer this information into the modeling to be able to scale up these findings. Just few words before going to the results. Few words about the experimental practices. So as said, this study or field experiment has continued now for 4 years. So we are really in the beginning. As Nico said in the previous presentation, it takes decades to see big effects. So we are really in the childhood of field experiment. About the principles, we had minimum tillage, not a no-till, but minimum 6 centimeter topsoil light tilling, moderate fertilization, only nitrogen given, no phosphorus because there was plenty of legacy phosphorus there. Herbicides only in that one control. And then I have to mention that we had to make some compromises between kind of agronomical best practices and science, because, for instance, we grew barley for the whole 4-year period, which is not the normal and best practice in agriculture. Normally it's a crop rotation, but it would have been too complicated for kind of scientists then to study the changing plant species, and people had different study periods. Somebody studied 1 year, somebody 2 years, so we had to keep that. And so that means that we had to sometimes, or actually very often, prioritize research over the yield. There were sometimes campaigns going on and the yield was already, or we could have harvested. We postponed it for 2 weeks because somebody was measuring something. But that's the compromise. We cannot. I think then when these findings will be taken into practice, then the farmers are the best experts in really doing the farming in that way that the yield is optimized. We didn't do it. We had also, as a challenge, I would say, we had a large field. We had 60 plots, and I remember when we were planning this experiment, we were discussing that we can have maximum 20 plots, otherwise it's too laborious for our team, and then we ended up with 60 plots. So it means that some people had to choose kind of part of the experiment for their studies. And then the geese need to be mentioned. This is kind of landing airport for geese. In the spring and in the autumn there can be big amounts of geese landing there, and of course you know what it means for the cranes. But that's life in the field experiments, nothing to complain. Okay, now I run through all these triangles, squares there on the right hand side to quickly show the first results. So as I said, this is a 4-year experiment. Many of the data is in the computers of the researchers. They are processing and have provided me the first results for this meeting. Some of them are really fresh. This data shows the first, which is important, the yield impact. So this is after 3 years, so the last year's yield is not included, and this is part of Serena Cappelli's manuscript, this part of the yield data. So as you can see in the left-hand side picture, there is a negative trend with plant diversity and yield, and it's in a way it's understandable. There is a competition. There is not only crop species. It's not optimized only for crop, and even the plant seeding density is lower in the cover crop treatments, or it's kind of had to be a bit lower to allow the cover crops to grow. It's not significant in this case, but you can see the trend. And there on the right-hand side, you can see each individual cover crops or Anderson species we used, how they impacted yield. So there are a few that had really strongly negative impact on the yield. Some had slightly positive, maybe not significant, but some slightly negative impact. So that just highlights that it's really important to select the right cover crops or Anderson species. And there you can see the worst one in our experiment was alfalfa. It grew so strongly that it completely overgrew in some plots barley, and it was the worst case scenario for farmer in this case. So good selection of species. And just one word about the health. It's in Serena's manuscript, and she did also, in addition to the field where she monitored fungal disease rates on the leaves, she also made a pot transplantation experiment where she had diverse soil and moved the pots between plots with different above ground and below ground diversity, and with that way she could find out that there are the above ground mechanisms that affect the disease kind of pressure, and there was a slight kind of reduction in disease rates in some of the Anderson species. Then about the soil processes, as already really thoroughly explained by Nico Eisenhauer, we also had this, and as we followed the same logic and the logic that has been published in literature in many cases for other ecosystems, so that the plant diversity, our hypothesis was that the plant diversity affects the below ground diversity, microbial biomass, and kind of increases this kind of network complexity and carbon use efficiency, and that would then affect the soil carbon sequestration. So these were our hypotheses. So these are data from Rasmi Shestra's PhD thesis. Rasmi is here. You can talk with her later on the coffee break if you like. And she has studied all the 60 plots for microbial biomass and carbon use efficiency, and also microbial community structure, fungal, bacterial in roots and soil, but that data is not shown here. But there you can see that the microbial biomass is significantly increased in higher biodiversity treatments. Soil respiration is not, but the plant growth has a trend to increase, as well as the carbon use efficiency has a trend to increase by increasing plant diversity. So even though not 0.05 significant, it clearly shows the same direction that was shown in Jena experiment results. So in a way that supports our original hypothesis. Then Luis Domeinos Horta, who is a postdoc in Annalisa Laines groups in Zurich, he has been studying also carbon use efficiency, but this network complexity. So he has studied community structure and then performed network analysis how these community members, in this case, this data is for bacterial community members, so how they interact and how the network complexity is affected by the plant diversity treatments. So there it's complex pictures, but to summarize that, in the right-hand side there you can see the red and blue kind of circles. In the red, they mean negative correlation if there is one species and another species. If their abundance correlates negatively, it's a red connection, and if they correlate positively, so if one species affects positively another species, it's a blue line, and this positive negative response ratio is a tool that can be used to describe the complexity and network properties. And there it's shown that these positive network properties are increased in higher plant diversity treatments. So also supporting the hypothesis of increasing below ground kind of microbial diversity and network complexity. Okay, then we had originally a strong focus on soils, but then we also studied fauna above ground and in soil. And this work is done by Paula Tits and Juha Mikola, who are here in the audience probably as well. And they studied soil fauna. Here is only nematode data shown, then on ground surface fauna, and then within vegetation fauna on two growing seasons. And to summarize here, on the upper graph show that the within vegetation fauna, if there was no cover crops, it's just monoculture on the left-hand side in the image, and then the polyculture means one of the cover crop treatments. So if there was something else than barley alone, so there is a positive and significant impact in the above ground arthropod community structure. On ground surface there was a slight negative trend, and on soil nematodes there was in the autumn there was a significantly positive impact on plant diversity on soil nematode community. In the summer not, so there was a seasonal, or summer it was, you can see there is probably a slight trend but not a significant difference, so showing a seasonal impact, which is obvious. And on the left hand side you can see the some summarized change directions of different faunal components. And Paula is around, so you can discuss with her more on the lunch break. Then greenhouse gas measurements were an essential part of the study, and they were conducted by Finnish Meteorological Institute. Stephanie Gerin is the PhD student working on it. She's not around here now. She's on another field experiment currently. They were measured using these light chambers, and there on top you can see them, and then on the right you can see how they were shaded differently to get the light response curves for different treatments. And this sampling campaign lasted for 2 years, including wintertime. And there the net ecosystem exchange data is shown in the next slide, which includes respiration plus photosynthesis, so it's the net exchange within the chamber. And if that value is negative, it reduces atmospheric CO2 levels, so it's a carbon sink, and if it's positive, it's a carbon source. Here you can see the first results, and as you said, preliminary results highlighted, as all these data are non-published, whereas Jena experiment had published, 20 papers in Nature, and so none of these are published, so please regard them as confidential within this room. Okay. Yeah, but anyway, these are really preliminary results, and many of the researchers just provided them for this meeting so that we can see the overall outcome already now. But anyway, here you can see this net ecosystem exchange data, and I have put these red squares in the areas where you can see the clear difference between cover crop treatments and barley alone. So during barley growing season, there is no significant differences. The barley grows so strongly, and the undersown species are kind of masked. The effect is smaller compared to barley alone. But when the barley harvest and barley growth reduces, then the cover crops still continue to photosynthesize, and you can see here the impact. And that was as expected, and Stephanie is working on the carbon accumulation data over the whole period. So they have tools to model now the whole growing season carbon budgets. Now we can move to economics. So there were also many other kind of measurements going on, routing depth, route dynamics, many priming experiments were conducted, many other things. So what we are doing on kind of natural sciences, chemistry, microbiology, physics, so on. But then those data, they are all delivered then to people who can do these estimations for other aspects. And Sanna Lötjönen is around here and she and Markku Ollikainen are in charge of the economic research. And of course there the aim is to study the question what is the profitability of carbon farming. And they have like two approaches. The first question is if more carbon is sequestered to soil, is this enough to is this already profitable for the farmer? And there the logic is that increasing carbon content increases the productivity and then the yield. And is that already enough to give profit for the farmer? And then the second question is that if that's not enough, then how to compensate? How is the carbon crediting counting going on? There you need to take into account the additionality of carbon and how long it remains in soil and so on and so on. So here are now the first results from their studies and kind of example of their results, not the final results. But here is the logic that carbon stock increases that lead to increasing yield, and then with different farming practices, fertilization levels, it's possible then to estimate how much that increases the yield, and then it's possible to calculate the profitability just simply from these factors. How much extra costs cover cropping causes for the farmer and how much extra benefit is obtained. So this was one example, and this work goes on the economic team. Then there is another modeling component led by Finnish Meteorological Institute. The previous team is working at the Helsinki University. Finnish Meteorological Institute team's aim is to include biodiversity into the models, and that's of course not an easy task, and it's currently not included in hardly any models in this context. And how they try to do it is that they use plant soil dynamic kind of sticks models, and the aim is that they constrain the parameters with the plant diversity taken from the plant diversity treatments. And in this case, they have leaf area and green area index data, net ecosystem exchange and productivity data, and yield data that they are working with. And of course, the aim is that with this extension from experimental data to model, they can then extrapolate the findings into regional scale and help farmers in their decision making. And this result is an example of how they process currently or proceed currently with this improve. Thank you, 2 minutes. Yeah, good. There you can see that the black dots are the measured values for leaf area index and green area index, and the red zone or the confidence area is the improved calibration of that model with the biodiversity parameters. So in this case, for instance, it shows that it fits better with the measured data, and with this path they can continue then to improve the model, also to model soil carbon accumulation. Okay, now the final, which was in the title, that was promised half a year ago, and unfortunately the carbon was mentioned there. But luckily the data came, but very late last Friday we got the carbon data, organic matter data we got last Monday. So this is really preliminary, and no data analysis is done, just plotting. And there you can see that, well, first of all, the circular graph is a very spectacular. I don't know if it's useful, but outside circle, the green one shows that if the carbon or organic matter content has increased during the 4-year period. And now remember, we are talking about 4-year, and Nico Eisenhauer said that it takes decades. So we are in the early, we are the children of the Jena experiment. But there you can see on the top, 0/4 means that the bare fallow treatments, none of the 4 plots had increased organic matter. Then if you turn clockwise, 2/12 are the barley-only plots. Okay, I'm over time now. Few minutes, 1 minute or 2 minutes. 17% of the barley-only plots had increased organic matter content within the first 4 years. And the rest, 44, so 12 out of 44, so 27% out of all our cover cropping treatment had increased organic matter content. So I would say we don't have significance. We are in the, as you see the Jena experiment data, our diversity level stops at 8. So we don't expect big differences, but there is kind of positive trend towards potentially increasing soil organic matter in our experiment. I don't take home messages too long as I'm over time. One take home message is that maybe I could say that the farmers, it was mentioned in other talks here, that the farmers know their hands feel the soil, and I think they are far ahead on compared to the researchers. For us, it takes a lot of time to show what their hands feel. So we are working on it, but we need long-term experiments, and we need organizations that fund those experiments. Nobody can do them alone. And it's really big teamwork. We need multidisciplinary studies to study all the aspects. Thank you. Thank you.
Thank you, Jussi. I will join the stage with you, but I think we are still in time, so we can take maybe 1 or 2 questions from the audience as well. I have one question in chat, but maybe we can take first from here.
Jussi Knaapi, I'm a carbon measurement man in Finland. We have a trial in southwest Loimaa school farm dealing with the same issues you studied very well here. Now my question is, we know that our yield capacity is higher than you were able to achieve in this trial. So what would you think, what are the main stress factors which has been affecting, because if I understood right, the yield was not that high actually, and I think it has something to do, the stress factors, how the carbon accumulation also has functioned.
That's a really good question, and as I said, we really didn't optimize our work for yield, meaning that in some cases, for instance, we saw with our bare eyes that the grains had already fallen down before we had time to collect it and so on. I cannot fully answer this question. Only thing is that we have rather small plots. There are quite a lot of disturbance side effects. For the yield, it's not optimal, and I think that's something. I must say that this is something that the farmers do better than we. So and I would say that it's kind of next step to then also transform this to the optimal farming. There are other people who could answer this probably better, but they are not around here.
Thank you. Maybe we take once more short question from the chat. If there is something you would like to add to this, someone is asking that how much these climate conditions are affecting to the soil carbon content, well, by increasing plant diversity. I mean, while you are increasing plant diversity in the field. Then the main question is that are the same result possible to achieve in Helsinki that we were seeing from Jena experiment? So comparing Helsinki to Jena, do we expect similar result, or is the climate condition affecting? I think this was the main point of the question.
Well, I don't see any reason why we couldn't see similar direction in Helsinki than in Jena. I think the bigger difference is that Jena is a grassland experiment and ours is an agricultural experiment where, for instance, every year we made a tilling. We kind of stopped the plant diversity and resaw everything again. So they didn't have time to kind of develop, like probably in Jena the communities develop over a long time. So in a way it's kind of 1 year cycle, new sowing of all plant species. Because if we would leave them grow, their balance would change a lot, and in the end we wouldn't have any yield because our crops would dominate. So in a way, I would rather compare. I mean, I don't think the climate impact is not a big issue. Of course, we are much more north, and we have longer winter and so on. But I don't see why it would not work here.
Okay. Now I think we have to move forward in the program, but please, please ask Jussi afterwards. Thank you. Thank you very much, Jussi. And I really appreciate this holistic approach that in these study designs that we heard both from Jena and from Helsinki. And I think this was something that was hoped in the morning session, at least. Ivo then pointed out that we really need to study the wholes and not the separate things. But as Jussi said, farmers do it better. And now after these 2 longer keynote speeches, we will have 3 shorter comment presentations to comment these what we have heard so far and to bring another perspective into conversation. So first comment speech is by Tanya Santalahti, who is from the Baltic Sea Action Group, and she will give a farmer's perspective to the holistic approach on farm level. Welcome, Tanya.
Thank you. Hello, everyone. My name is Tanya Santalahti, and as Elisa said, I work at Baltic Sea Action Group as senior specialist, and I am also a farmer. Now, I'm going to ask everyone to just get up from their seat. Thank you. Give me a few shrugs. You can do this at home as well. All right? A big stretch. And then you can sit back down. Perfect. Now that we have blood flowing into our brains, we can concentrate on a holistic approach to healthy soils from a farmer's perspective. So we've heard so many benefits already about how healthy soils can be measured and monitored. They can be observed and experienced. And some are more tangible than others. I've actually categorized these benefits into 4 boxes. So the ecological, the economic, the health and community or societal benefits. And there are probably other ways to categorize them, and this is not a complete list. But the fact is that they all weigh in the decision-making process on the farm. Now, healthy soils typically have a sufficient or even a rich amount of organic matter and soil organisms, which improve soil structure, aeration, water retention, drainage, and nutrient availability. Fertile soils are valuable for a farmer. They have the ability to produce higher quality crops. Now, quality is a term that actually Ivo brought up in the morning. Quality is something that we have to concentrate on, and it actually brings benefits for the farmer. Now, biodiversity plays a crucial role in maintaining ecosystem functions and services, such as pollination, pest control, and soil formation. And by working with nature instead of against it, I know this is a quote that has been used so many times, natural processes actually help in pest management and other farm functions that currently require more damaging techniques to soils. And water retention actually allows you to reduce the amount of runoff, sediment, and erosion in your fields. That is a concrete benefit you gain. this actually also creates resilience to extreme weather events. Now, there are actually two big ways that healthy soils can help in climate change. It's the adaptation, so the building resilience, and it's mitigation. Now, in the other parallel session, I know that they're discussing about measuring and monitoring carbon sequestration. Let's not go into that now. But I know that carbon sequestration is actually being discussed in coffee table discussions between farmers. It is a benefit that they actually value. Now, as we heard from Jussi, the economic benefits of healthy soils is a controversial question. But it is still indisputable that healthy soils have the ability to make farms more productive and provide more nutrients for the plants. And as I mentioned before, healthy soils actually bring the resilience towards weather extremes. And this in turn helps in risk management. It doesn't mean you can control all the risks, but you can manage them better. And healthy soils can actually increase farmers' profit margins by reducing labor and expenses for fuel and actually optimizing inputs. And as I said, carbon sequestration allows us to mitigate climate change. And even though we're afraid to discuss carbon markets, I think it's a function that we need to take into account. And it already does provide income and additional income for farmers. And I hope that someday we will have a functioning and robust system to help in this and aid in this endeavor. If we talk about healthy soils in a bigger picture, we know that a functioning food system provides self-sufficiency for a community, and this provides safety even in the face of climate change. From an individual perspective, looking at your soils makes you steward of the land. It makes you a forerunner or a trendsetter. And you can actually pave a path for others to follow. You can influence that systemic change in the food chain. You can meet a change maker in your community. And I am certain that a farmer who observes a healthy, functioning soil feels pride and motivation in his or her work. And Maria Ösch said it beautifully. If you can visualize the change in your soil, you can visualize the health of your soil. It actually builds the relationship you have with nature. And in health issues, we actually have also the physical health benefits. You can actually reduce your exposure to chemicals. You can improve the quality of your life. And these all come from healthy soils. Let's see if the clicker works. Sorry, now I missed the slide. But to end this session, I just want to say that even though we know all the multiple benefits, even though farmers can experience them and know them, it doesn't mean that we are not afraid of them. So change of the unknown is always something that can be feared, but we have to see the opportunities, and we have to be ready to take that first step, because that will bring us the benefits, and we'll learn, and we're willing to go forward. Thank you.
Thank you so much, Tanya. This was a very important perspective to this conversation to bring to the stage at this point, I think.
Thank you.
Do we have questions from the audience? I think we have time for one or two questions or comments. Okay, I think we will move ahead in the program, because we also I don't see any questions in the chat, and we can catch a bit in time. Next, I would welcome to the stage Liisa Pietola, who is a leading specialist from Sitra and also a board member in EU Soil Mission. Welcome, Liisa.
Thank you.
Thank you very much, Elisa, and good morning for everybody.
Yes, I will wait my slides there. They are coming, and meanwhile, I just say that my background is soil science. I'm farmer too, but really much I have focused on agricultural soils, and this is my great pleasure that I can today comment on this very, very comprehensive presentation we just have heard. And also yesterday we have had very good messages, and this is really great event we are having. So my title is so that I will kind of answer to the question how to find win-win solutions by soil management, and by the question that will touch healthy soils for climate, biodiversity, and water quality and water. So now I will bring kind of the third element on this picture. Tanya already touched water retention, I heard that word, but not before so much. And of course, water is so essential for our food production and healthy soils, and therefore it's good that we brought this word also into the context. So I'm working in Sitra, which is a Finnish innovation fund, and there I worked for sustainable transition of agriculture. And in our team, we really are looking for healthy soils and, of course, for biodiversity and climate mitigation and adaptation, and especially through circular economy. And agriculture and regenerative agriculture is certainly circularity. And so this is very, very good context to discuss about healthy soils and circularity in agriculture. And so there are a lot of win-win solutions. And the main thing is that we could be well here under the planetary boundaries, which have also been in discussion. And as Elisa said, I'm also a member of EU Mission Soil Deal for Europe, board member there, and this is very much needed to discuss about today how our soils are functioning for the better future. And so if we look what yesterday Vice Director Magda Kopczynska said, that our soils in Europe, they are not at all in good conditions, and 1/3 of our soils could be say that they are healthy. So there are many problems, and so this is really time to discuss and have good research and good management practices to solve the situation. So we do have many solutions to take with soils, and therefore I am very happy to present these objectives of soil mission. So there are plenty, 8 targets, but there is none word water. There is no target for water, but so first when I saw these 8 targets, I thought that, But then if we look, reduce desertification, conserve soil organic matter content, prevent erosion, and then improve soil structure and biodiversity. So there it is. It comes from all these different targets, and also this stop sealing, soil sealing. This is one target too, because when we seal the soil, we will kill the ecosystem services and soil functions like infiltration of water and gas exchange and etc. So if we combine these all missing targets, there is a water in. And like Ivan said, that study the holes. So I put this picture for that. And this is good that we can now maybe focus a little bit on this picture, because there are many elements we were discussed just this morning. If we look, this is kind of, this is small carbon cycle, but this could be also small water cycle, and this could be also small nutrient cycle, soil cycles. And this, if you look, the photosynthesis I put there first. This was also what Adam said yesterday as a farmer, that we need to look photosynthesis, so both below and above ground biomass, and photosynthesis is a main driver for that. So we need to look the needs for photosynthesis. Then we just heard about the many good solutions based on crop rotation or crop diversity, mixed cultures, and so we will really need to have different type of crops during growing season, mixed or in rows or year after year in crop rotation. Yeah, all is good for root biomass and root exudates and biomasses of microbes and so. And why this is so important, because soil microbes, fungi, hyphae, and microbiological exudates, they really build the structure. So, and make the aggregate stability good, and that will prevent erosion. Like here in Finland, we do have a lot of clay soils, fine textured soils. We need to have a very good soil structure to enhance water infiltration, but also to control erosion, which is related to water quality. And then, of course, nutrient recycling and soil biota, it is very, very beneficial for all these four elements of this big picture. So I just will focus now on soil structure. This is really important. It's really important to look soil pores, pore size differences, pore continuities, because this is the basis of soil functions and also for all these good things we have heard. So we need to have sustainable water management. It has not yet said here. So we need to offer air supply, usage aeration, and water supply, and then comes the nutrients in this order. So due to the climate change, we do have excess water also. We are suffering for desertification, but we do have excess water. So we need to have a drainage system to lead the excess water away from big pores so that the roots can breathe and biota can be alive. So this is really much, it's a lot of importance. And then comes crop rotation and carbon sequestration and biodiversity, which will have been discussed already. And the third management practice required is reduce tillage, as said, and avoid compaction. I have not maybe heard that word either. So all these together are essential, and especially in field ecosystem, which is different from natural ecosystem because it will give food in short season. Like here in Finland, we just have 2 months season or so. Yeah, 0 minutes, so I stop here. By these 2 elements that we need to focus on, both soil carbon and biodiversity, without forgetting sustainable management, and then find indicators to show the progress for farmers' economy, for inventories of national greenhouse gas elements, and so. So we need specific indicators for different soil types, for different soil conditions, for different management practices. Thank you very much.
Thank you. I think we have time for a couple of questions. If Liisa, you can stay here. Yeah, well, I think we have time to take questions if there are in the audience. Any follow-up comments? I think it was very nice that you brought up like these water infiltration so much, and also these different cycles of different nutrients. I really like. I think we need to remember all the time that of course these conditions and how the water is problematic, it might be very different in different parts of Europe. So this was quite a lot in context of Finland, but not only about the context of Northern Europe, and of course this meeting is Northern Europe. Yeah. Now we actually have a couple of questions. Let's take from back there.
Yeah, this is Nordic meeting, so in that way it was relevant.
Yes. Yeah, I have a question about the drainage and irrigation, because of course it's first you drain the fields and then you need to irrigate them. So do you have any idea to like where to drain the water to, like with the creating dams or anything that you then can use it, the same water again?
Yeah, we needed to pay attention to store the water, excess water, when we are draining it to we can have them in big ditches or these wetlands, or so that we can then use that water later on when we have this drought period. Like here also, we will have them. So we need to drain and restore and then irrigate. Or then we have also the subsurface drainage systems where we can adjust the water table if the soils are capillarity enough. So there are plenty of kind of management practices we should focus more to have both air and water supply for our plants.
We can take another.
Jussi.
May I pinpoint one thing? We talk a lot about minimum tillage. Actually, it can be more intense than some other tillage, not to talk about no-till. Minimum tillage sounds nice, but it might create a compaction layers right beneath the surface. And then we know as Finnish farmers that we have these winters, we actually may increase the erosion, even that we minimum tillage. The main thing is exactly what Liisa told. We need to manage the soil in the way that the infiltration goes up to the level where we don't get this erosion risk.
Yeah, this is very good point you raised, that there are plenty of management practices, but it is about how you use them. So, of course, if you go and have some tillage during wet conditions, and it will destroy the pores. But still we need to kind of reduce tillage and not just kind of mix soil and soil a lot. I just visited the northern part of Finland, and I saw this wind erosion in fields which were just been sowed for spring cereals, and I saw this wind erosion because of excess soil tillage. So we need to get rid of that too. Thank you.
Thank you. I think, did we have a third question? We can take one more quick question. If you also answer.
Thank you.
Shortly.
You've mentioned to find the indicators and to show the progress. I think that is very important to show the progress for the farmers, for the society. And in the spirit of keeping this simple, what are some of the fundamental indicators to measure and to show?
Yeah. Okay. I would love that farmers would have, and they report before they are starting the season, they report what they will go to sow and by what tillage practices, and so there are already calculators. And for our administrative people, they will tell what they are going to do, and later after the season they will still fix what they actually did. So there, if we could have for these given soil types and management practices and crop species kind of emission factors, like for greenhouse gas emissions, so that with models, with good empirical data, we still can have that to show in the tables then the kind of estimates for them, their emissions or carbon sequestrations for the given soil parcel. That would be kind of the way I would see. And also for biodiversity, why not? We just need to have these indicators so that we can show quantitative numbers, because otherwise our policymakers, they won't lead up to the kind of direction which will have good impact for soils, for us, for nature. Yeah, so I see. Thank you.
Okay, thank you. Well, maybe one more applause. Thank you to Liisa Pietola. And next, our last comment speaker in this session before lunch, we hear from EU Soil Observatory from Cristina Arias-Navarro.
Yes, thank you. Good morning. I'm Cristina Arias-Navarro. I work for the European Commission for the service that is called the Joint Research Center. that is the Commission service providing knowledge and scientific support to EU policies. Today I'm going to speak about the EU Soil Observatory and how we provide the soil health knowledge to support the Green Deal and, of course, soil policies. So we were talking now about indicators, and I will speak a lot about indicators. So let me just start by saying that setting thresholds indicators is extremely difficult, being the conditions of soils at continental scale very different. Setting thresholds can be quite controversial in some cases, but we do what we can. So you have here, for instance, to see the diversity of soils, the Soil Atlas of Europe. That is some of the products that we produce in the EU Soil Observatory. So GRC, a Joint Research Center, has been working for many, many years providing data and knowledge about the European soils. We do that through the ESDAC, that is the European Soil Data Center of the Commission, that has been operational now for 20 years. So building on that, the Commission launched 3 years ago the EU Soil Observatory, expanding like the data center capacity of GRC, especially enhancing the soil monitoring system we have at the EU level. Our soil monitoring system that is based on LUCAS, the Land Use and Land Cover Area Framework of the European Commission. Then another very important component of EUSO is the research and innovation. GRC remains a research center, so we put like a lot of effort on providing data and analyzing the data and providing new scientific insights into EU policies. Another very important component is that EUSO aims to be inclusive, and we do that through the stakeholder forum that we organize once a year. This year, we will meet in Madrid in the EU Soil Week, organized with the Soil Mission, and on the occasion of the Spanish presidency. And here in EUSO, we operate like different technical working groups. We have currently 6 working groups. We work on soil erosion, soil pollution, soil data, monitoring, soil biodiversity, and last year we launched a new technical working group on soil organic carbon reporting and monitoring, reporting and verification, also in support of our colleagues in DG Agri, because we report to the carbon expert group. And then finally, in EUSO, we have the opportunity to give users an overview of the status of soil health and the condition at EU level. So we have just launched the soil health dashboard. It comes in support of the new upcoming soil health law and the soil strategy for 2020. It also supports the Horizon Europe mission on soil, because in the mission, soil monitoring, soil health monitoring is a very important indicator. So I encourage you to go to the web and check and use it, and you will see there the current degradation processes that are going on at EU level based on several indicators. We present the data in a spatial way. We call it the convergence of evidence map, and you will see that in some areas more degradation processes are accumulating. So in the map, the red is the map is the worse the condition. And we estimated that 61% of our EU soils are in an unhealthy state. So now, a very important topic, the selection of indicators. We were just talking before about that. So this is a recurrent topic, something that is coming back again and again. I need to be a bit careful here. So with the scientific community, many times proposing indicators that are very robust, are very scientifically sound, that are the ones that they should be, of course, but they are not harmonized or homogeneous at the EU level. So we here need to be a bit pragmatic and use what we have. So we saw in the map is the data that we currently have available at EU level in an harmonized way. This means that new indicators that may be more scientifically sound need to be provided also in an harmonized way in order to have a coherent view of the status of soil health in the EU. And this is only possible if you have a constant flow of data coming. So as I said before, we do that with our Lucas soil survey that is based in 25 sites across the EU. We have a range of surveys already, and this allows us to calculate trends also over time. And now the ambition is in the future to expand this soil sampling capacity. This is what the new soil health law is aiming to propose, to have EU soil monitoring system integrated with national soil monitoring systems, and maybe using the transfer functions to make the data comparable. And yeah, this is what, hopefully, if the law is adopted, this is what we are going to see there. And yeah, with saying that over time, if we are able to track and how our soils are doing, if they are improving, will be a clear indicator of the success of the law, also the strategy and the EU, the Green Deal policies in general. So yeah, that's all. Please go to our web to find out more and more detailed information about EUSO and the soil health indicator. Thank you.
Thank you, Cristina. I think it was very good that we have now also heard like what is needed in the EU level, and also as we heard in the previous talk about EU mission. Do we have any questions from the audience at this point? I think we can take again one or two before going to lunch. There is one.
Thank you for your presentation. I'm Timo Taulavuori from Puutarhaliitto, Finland. I have one question about your map. There was no Finland, so...
Sorry,
so,
it's the screenshot, but please go to of course, Finland is there. Sorry.
Is it green, red or yellow?
Greenish, I can say, but go and check.
Thank you. But this is the atlas of soils. I don't see the. Sorry, is here. Is the soil types? Is not the condition of the soil.
Actually, that was my first question when I saw that once. Yeah, it was in this January. But this is very nice map. I like it very much. You can focus on Finland, and you can go even to your home village. Yes. So it's very precise, very nice. Thank you.
Welcome. And okay, I didn't have time to present everything, but we aggregate also the data at different levels, so NATS 1, 0, 1, 2, so municipality level. You can also see that is where action must be done to reverse the unhealthy soil condition.
One more question we can take, and then I think we go for lunch.
Yeah, thanks so much. I was just wondering about, because it sounds like, about the indicators and the data, you said like it might not be the best scientifically sound because it's trying too hard. So what are the problems or the the problems in that balancing between the data that's available in all of Europe versus the data that is actually showing what is important?
I don't say it's not the best because we really provide very scientifically sound maps and information at EU level, but it's EU level. So many of the indicators are based in our local soil sampling, but we do modeling. So, you know, there are some uncertainties with the modeling. So, of course, if you take samples in your field, you analyze them and you come up with all your indicators, you will know how your soil is doing. But from a top-down approach with the law, we cannot set up this set of very specific indicators, thresholds, and here maybe we say for erosion, 50 tons of per hectare, but at EU level, maybe in the Finnish soils, the number is very difficult. Sandy soils, Mediterranean soils, you cannot compare with the Finnish soil. So this is what I meant with this, that it's not that it's not the best, that EU scale is the best, but we need to be a bit careful also. Yeah.
Thank you. I think we close this session now and maybe give one more applause to Cristina first. Thank you.